Hi, this is JLN Murthy. Success is built, not gifted. Let us master maths step by step. Important standard integrals, part 2. In the previous episode, we have covered part 1, wherein some of the formulae we have discussed with explanation. Now, in this part 2, we are going to cover 3 more important integration formulae. A comprehensive guide to inverse trigonometric and logarithmic integration formulas, essential for mastering advanced calculus techniques. Formula 1. Integral of dx by square root of a square minus x square. This we are going to solve using substitution method. Substitute x equal to a sin theta. This transforms the radical into a simpler form, and when x is a sin theta, we have dx equal to a cos theta d theta. Now the expression root of a square minus x square, if you take it, substitute x is equal to a sin theta, then x square will be a square sin square theta. A square minus a square sin square theta, a square taken common, a square of 1 minus sin square, which is root cos square, and eliminating root we get a cos theta in the simplet form. Now we know that sin square theta plus cos square theta equal to 1 is an identity, trigonometric identity, very important one, and reduce integral of d theta equal to theta plus a constant of integration c. Fine. Now this integral simplifies completely. If you substitute back theta equal to sin inverse of x by a, then result is integral dx by root a square minus x square equal to sin inverse x by a plus a constant of integration. That's it. Okay. This appears very frequently when dealing with circular or elliptical geometry and inverse trigonometric functions. Okay. Let's move on to second formula. Formula 2. Integral of dx by a square plus x square. How to solve this type of formats? Okay. Here let's substitute x equal to a tan theta, and dx will become naturally a secant square theta d theta, and the expression a square plus x square will reduce to a square taken common 1 plus tan square is secant square, therefore a square secant square theta. Now it is simplified to 1 by a of integral d theta, which is 1 by a of theta, and theta is tan inverse x by a, therefore you get the integral dx by a square plus x square equal to 1 by a tan inverse x by a plus constant of integration, that's c. Okay. Next. Integral dx by x root x square minus a square. It looks a little complex, but once you substitute and simplify, you will understand it is a simple part of it. Okay, let us take a simple substitution, x equal to a secant theta. Good. Then dx will become a secant theta tan theta d theta. Fine. Then expression, if you take only root of x square minus a square, that reduces to a tan theta. You know, secant square theta minus 1 is tan square theta. That's why you get a tan theta. Now, once you substitute all this, dx has already become a secant theta tan theta d theta, and in the denominator I have x as a secant theta, and the expression root x square minus a square as a tan theta. So a secant theta into a tan theta is a square secant theta tan theta. Numerator you have a secant theta tan theta. So 1a will remain in the denominator, that is taken out of the integration. You get 1 by a integral d theta. Integral d theta is nothing but theta. Therefore 1 by a theta. Therefore having taken x equal to a secant theta, theta will become secant inverse x by a. The in finality you get, yeah, you can see in the next screen. Result is integral of dx by x root x square minus a square equal to 1 by a secant inverse x by a plus the constant of integration. The secant substitution is ideal when dealing with expressions of the form x square minus a square. This integral yields the inverse secant function, which is less common but equally important in advanced applications.